All right. Hello, everyone. It's Kalen Langley in ECE 275 Digital Design. This is a term project to design a stopwatch in VHDL that counts from 0 to 59 and loops back to 0. The stopwatch will output its count using two separate 4-bit signals, one which represents the digit 0 through 9, the other representing the tens digit 0 through 5. We will simulate the stopwatch functionality in Model Sim and demonstrate its behavior based on start and reset controls as well. So here is the paper design of the simulation. So by showing you this, I'll walk you through how this 0 through 59 counter works using two separate 4-bit counters or registers, one for the units place and one for the tens place. We have three inputs. The start enables the counting when high. We have the reset, resets both digits when active or active high, and we have the clock signal to drive the counters. I built this using the help in Quartus using the RTL viewer. The counting mechanism, digits count from 0 to 9, and the tens counter, or this register up here, counts from 0 to 5. We have a couple adders. It takes the current units register and adds a one constant with a carry in of 0. Yeah, carry 1 of 0 here for the units register and a carry 0 here for the tens register. The tens register counts from 0 to 5, like I said earlier. Practically, both of these are just an incrementer. We have equality checks for the tens as well as the units. This just compares if the current register equals 9 or 5, since we're counting 0 to 9 or 0 to 5 up here. When it does, it forces a reset to 0. I'll demonstrate that here in just a little bit. We also have a series of muxes that are used to select the incremented value or a reset, which is here, and that's VHDL's coding for hexadecimal or 4'H0, which is equivalent to 0. They also control the comparator start reset commands as well. As you can see here, the start hits these two muxes. This reset controls these two. We have a couple of registers, and it outputs the final 4-bit either units or tens. And then these are D flip-flops with a clock and a clear. Walking through the requirements for the design, when reset is high, the units and the tens registers are all 0. When reset is low and you have a active start command, with each rising edge of the clock cycle, it'll start counting. So for the units register, it'll begin counting 0001, another active clock cycle 0010, and so forth up to 9. Once you hit 9, with this conditional statement up here, it'll start tracking the tens place. When reset is low, you have a when reset is low, start equals 0. With each clock cycle, the sequence pauses, so that just tells us when you're not reset and you don't have a start command, we're not counting. When reset is low and the start command is 1, each active clock cycle, the sequence resumes. It either starts or picks back up from where it left off. This timer counts from 0 to 59 and resets back to 0. Again, this just details the 4-bit signal counts for 0 to 9 and the tens place from 0 to 5. At the bottom, I just drew out a couple examples of how this will operate. So at 0 seconds, all are 0. 5 seconds, the tens counter is all 0, whereas the units count is 0, 1, 0, 1. For 9 seconds, the tens out is all zeros, the units out is 1, 0, 0, 1. And for 10 seconds, the tens out is 0, 0, 0, 1, where the units out is reset back to 0. This diagram here just helps us walk through how these muxes operate and utilize to help us check whenever we're selecting either the incremented signal or the equality check. So say we start the command, everything is 0. So this output will come back here for the units. We'll increment by 1 with this condition here. So we're adding 1. It's outputted here. We're not 9, so this will be false. It will output A. So we've outputted 1 to here. We also have 0, right? Because that's where we started, to here. But with this start, we're going to select B, which would be the 1. The 1 goes here. As long as reset is low, we're going to output 1 to this unit register. And with the next active clock, it will count up 1. When we get to 9, we'll increment here. Technically, this will be 10. But since this is 9, we're going to use that select to select A. Or sorry, select B, right? If we select B, that would be this hexadecimal equivalent to 0. We push 0. And with the active start, we're still pushing 0. Without the active reset, we push 0 again. And the counter down here for the units out is reset to 0. On the next, or at that same time, the next active clock, since we are 9, we're outputting up here to this select signal. This one starts off initially at 0. So we're incrementing by 1, as you can see here. As long as this is not 5, we're selecting A. So as long as this is 0, we're passing 1 to here. Now, since this is 9, we're going to select B, which is this input. Start is still active, so we're selecting this input again. Pushing it here without the reset, we're going to push 1, and that will increment this tens counting register by 1. We also utilized Quartus with help of this design using the RTL viewer. I can demonstrate that now. Here's what we used to help us draw this paper design. It did take some time trying to understand exactly what was going on and how to step it through, but we were able to work that out as a group. Now, here is the code for the main stopwatch hierarchy. And we added several comments to help us understand what's going on. So we're declaring this entity stopwatch that has a port, which we map the clock, reset, start, and then we call our units out and our tens out programs that we also built. So this does have some it does have some modular components implemented in this design. And then there's some if statements to reset the 0 when needed, especially after counting the 9, and also in the tens place when counting to 5, it resets to 0. Here's the tens counter program file, as well as the units counter. Now, after we coded these different programs, we launched a model sim, and then we created a test bench. And we're going to utilize this test bench to test all the different conditions to make sure a stopwatch is operating as intended and is functioning properly. So I can pull up that test bench code real quick. So here's the test bench we created. And then down here we set the process and initially tell it to wait, and then activate the reset, start the stopwatch program for 700 nanoseconds, temporarily add a stop signal to check if it's working or not, and then we'll resume it. And then we'll add a reset command to check if it's working as designed. So here is after we already started it. I'll zoom in and step it through to make sure it's working properly. Initially, both counters are all zeros. Then we have a active high reset command, which nothing really happens because our units out and our tens out are already zero. Whenever the reset falls off, we enable the start. So on that next rising edge, we'll start counting from 0, 0, 0, and the units out to 0, 0, 0, 1, which is 1, and then 2, 3, 4, 5, 6, 7, 8, 9, and as long as that start command is enabled, which it is, it's going to progress to 10. Once we get the 10 and the tens place, we're going to count again, 0 through 9. So we have 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then finally 20. At 20, you have 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. As you can see here, you have in the tens place 0, 0, 1, 1, and the units all zeros. So at 30, we go to 31, 32, 33, 34, 35, 36, 37, 38, 39, and 40. And to 41, 42, 43, 44, 45, 46, 47, 48, 49, and 50. Now we should have one final full count. 51, 52, 53, 54, 55, 56, 57, 58, 59. And as long as that start is still enabled, you're going to reset back to the initial state of 0, 0, 0, 0 for both the tens out and the units out. So noticing that you still have your start and reset is low, you're going to start or continue counting. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we lose the start command. So whenever that falls off and you have that rising edge, it maintains that 10 value. So it's going to stay there for several clock cycles at 10. And then whenever it resumes, it will continue counting with that rising edge. So you resumed here, the next clock cycle, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. It will continue on in this process that we went through earlier until we either lose the start signal or we have a reset, which you can see here. So here we have 30. 0011 and 0000 for the tens. And then the units, sorry. The tens is 0011. Going to 11, 12, 13, 14, 15, 16, 17, 18. So, oh, sorry, we're not there. My count's cut off because you're 30. We progress 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. 40 and is 0, 1, 0, 0 in the tens place because you have 1, 2, and 4. So, okay, making sure I got my counts right. We do enable the reset here, and once that is enabled and you have that rising edge of the clock, it resets both counters to 0. As long as that reset is held, it maintains all zeros. The reset falls off with that enable start command still active. We start counting again. So at 1, 2, 3, 4, and so forth. And that process will continue as long as you run the simulation or there is a change in the reset command or the start command. It will reset it back to 0 or pause it depending on how those two states. All right, that concludes it for this video. Thank you everyone for your time.